Hello, everyone, and welcome to TigerBeetle, a show where we study this pretty exciting database called TigerBeetle and try to understand how it works. And well, the database is exciting for a variety of reasons. It is written in an unusual programming language, Zig. It doesn't allocate memory after startup. It is super resilient regarding storage faults. So even if, your hard drive returns garbage, TigerBeetle still stores your data securely. It doesn't have a data definition language or SQL. It comes with hard-coded the main model and many other things. Okay, so where are we at in our story? We are trying to figure out various parts of the code base which we've skipped on the first reading. And last couple of times, we looked at the clock, how TigerBeetle deals with time, how it uses clock, how it ensures that there is a monotonic cluster time even if the NTP is not reachable by the primary, for example. And I think we've mostly done with time. So today we are going to start looking at the state sync algorithm. So how a replica catches up with a cluster if a replica was far away from a cluster for a long period of time. But before that, I still want to go back to time a little bit. Because last time when we were looking at the code, there was a couple of suspicious places. And I want to return back to one of the suspicious places, to the asymmetric delay, to clarify that I was wrong and that one isn't actually buggy, and rather the code was doing not the thing which I expected it to do. So in terms of the code, we had in our clock estimated asymmetric delay, and I kind of didn't understand this function last time. So I read this paper, and now it makes much more sense to me. So let's open our browser, and not this window, but another window. Well, where is my mind? Where is my browser? I should have it. Okay, this is it. Okay, and figure out what actually is screen share, please. Okay, this is. Thank you, AD Super. You've saved this stream from being a complete disaster, because as much as I like to show off my new haircut, really we should be. Oh dear. We should be sharing my screen, and we shouldn't be sharing this screen. Rather, we should be sharing the screen which actually has interesting stuff on it. Okay, so let me quickly check. Okay, this is main display. Okay, so then it is on AW and OBC. Okay, so now I want to share this screen. Yes, I want to keep these changes. Okay, so now it should be better. And again, thank you very much for noticing this, because it would have been embarrassing. It happened before. It happened before where I went for half of the episode without screen share. Okay, so we had this estimated asymmetric delay function in clock.zig, and last time I kind of said that, hey, I don't understand what's happening there. Either I'm stupid or it is buggy. Well, as I've learned, the code is not actually buggy. And what is true? Well, I'll let you to figure out. Okay, so what I was thinking that code is doing. So suppose we have two replicas, and suppose that we got ourselves into an, actually let me say that this one is green. Suppose that we get ourselves in an asymmetric network topology. so that if we send the message from the red node to the green node, it takes, I don't know, let's say 100 milliseconds. But if we go in the opposite direction, it takes 200 milliseconds. So twice as long. Okay, so I was assuming that estimate asymmetric. Well, first of all, why the situation is bad? Well, the situation is bad because when we use round trip time to estimate pings, we naively estimate that the round trip time is like, sum divided by 2. And if we do this, we'll observe that our estimate for clock offset is actually off by 50 milliseconds. And I assumed that estimate asymmetric delay actually tries to deal with this kind of situation where we have persistent, stable asymmetric delay, stationary asymmetric delay, where going there is just faster or slower than going back. But actually, that is not what that code is doing, because you could not, in fact, figure out this situation. There is some kind of general theory of relativity thing happening on. Because let's see two pictures. So one picture is that we don't have an asymmetric delay. Path there takes 50 milliseconds, and path back takes 50 milliseconds, and then the clocks are synchronized. So this clock and this clock are exactly the same. What are we going to observe in this situation? Well, if this node sends a ping and times it with time t, then it arrives at time t plus 50 at the other node. It stamps it with t plus 50 and sends it back. So in other words, in this picture, whenever a node sends a ping and resends a pong, it observes that it receives its ping message 100 milliseconds after it receives a response, a pong, 100 milliseconds after it sent a ping, and the value inside this message, the value of the clock of the other replica, is plus 50 milliseconds. Now let's see an alternative situation, which is somewhat pathological. Let's say that delay there is 100 milliseconds, so it is twice as slow. But delay back is actually just 0 milliseconds, so literally zero, literally instantaneous. This is, of course, not realistic, but it is helpful to build an intuition why you cannot determine this kind of asymmetric delay by just measuring time. And then let's say that the clock on the green node are actually 50 milliseconds ahead of the clock of the red node. Now, okay, let's see what happens in this picture. I claim that from a perspective of either the red node or the green node, it is actually indistinguishable from a previous picture. Okay, so let's say that red node, well, no, it's not plus 50 milliseconds. Let's say it's minus 50 milliseconds. Okay, so, well, no, this is going to be confusing. So let's say that it is plus milliseconds, but I want to swap these two. So sending messages there is instantaneous, but sending messages back takes 100 milliseconds. Okay, so red node at time t sends a message to the green node. Because this leg of a trip is instantaneous, it arrives at a green node at time t. And because green's clock are 50 milliseconds ahead, this message gets stamped with t plus 50. And then at time t, it is sent back. So it arrives back at the red node at time 100 milliseconds later, at time t plus 100, and it still has t plus 50 stamped inside. So let's actually write this down. So in this situation, whenever red node sends, it's send at t, receive at t plus 100 with clock t plus 50. The clock are t plus 50 because, well, it is t here and there, but it takes 50 milliseconds for the ping to travel. And the same happens here. So as I've just demonstrated, the red node on the right, in the right picture, observes exactly the same thing. It sends a message at t, receives response 100 milliseconds later, and the clock inside the response are 50 milliseconds off the sending time. Okay, now let's say what happens at the green node. So it sends a message at time t. So this message arrives at the red node at time t plus 100 milliseconds. But because the green nodes, okay, let's actually start writing it down. So we sent at t, receive at red node at t plus 100. But the red node clock is 50 milliseconds behind. So the message, although it gets received at t plus 100, it gets stamped with t plus 50. And then it is sent back. So at t plus 100, it is here, and 0 milliseconds later, it is back at our node. So we actually receive it at t plus 100 as well. And we see that the time is 50 milliseconds forward. So in other words, you can't actually, using just the time management, you can't actually, okay, and oh, wait a second, where is my OBS? Is it still running? Okay, it's still running. Okay, I am lost in my Windows. Sorry about that. Let me quickly get back. Okay. No. Oh dear. This is so complicated. Okay. Now I'm more comfortable that I'm actually fully online. Maybe I've lost the chat again. Why this is happening to me? Okay, never mind. Okay, anyway, what we figured out today, what we figured out right now is that actually, yes, you can't distinguish between those situations. You can't actually detect asymmetric delay because no matter what asymmetric delay is, you will be getting the same time management for your clock. So this is not the model which underpowers asymmetric delay function. Instead, what is actually happening? So the picture is this. Normally, we don't have an asymmetric delay. Normally, the message gets there and back in 50 milliseconds. But sometimes a single particular message could get delayed. So, okay, let's say we send there in 50 milliseconds and we expect to send here in 50 milliseconds, but here, maybe we dropped a packet. Something happened, wires get crossed on the router, maybe some interference in the wires, like whatever, or maybe like, even simpler, maybe this node was particularly busy, so before it could have sent us a request, it had to send a different message from the network, and it was just like busy sending the packet. So anyway, so like normally it takes 50 milliseconds and 50 milliseconds, but like one time we got 200 milliseconds on the way back. So in other words, the stationary situation is without delay, but occasionally something gets slow. And if something gets slow, then of course it's not going to get like, universally slow there and back. It probably happens either on the leg forward or on the leg back. And this is what the asymmetric delay code is doing. So the idea is this. So normally you expect the round trip time to be 100 milliseconds. And then suddenly for this particular packet, your round trip time is 300 milliseconds. So if normally it is 100 and you got 300, then you got 200 milliseconds of extra delay. And the question is, was this delay on the forward leg on the trip or on the backward leg on the trip? And this is what asymmetric delay actually does. So you see that we have one-way delay for like our current sample. And then we have one-way delay from the current epoch. And a reminder, the way the clock works is that we have epoch, which specifies the clock we are currently using, and then we have window, where we accumulate new information. And the rule is that inside the epoch, we include the sample with the lowest round trip time. So this is our current round trip time, and this is our lowest round trip time. And if our current round trip time is significantly larger than our minimal round trip time, then we know that a delay happened for this single packet. And depending on whether the clock offset is larger or smaller than we would have expected, we can infer whether the delay was on the forward leg or on the backwards leg and adjust it appropriately. Okay, so that was all about the clock. And now finally, we can get to state sync. Okay, so let's get back into our beautiful browser and do an intro of the state sync. And also, once again, we do a refresher of how the data is stored in the TigerBeetle. So we have time. You can't get away from the clock. We have time. And over time, TigerBeetle adds prepares to its, no, that's like very thin prepare. Over time, TigerBeetle adds prepares to its log. Now, log is actually some physical region or in the data file on storage. And because everything in TigerBeetle is limited, we actually don't allow the log to grow indefinitely. So this log is, I think it is 124 slots total. Okay. And then inside those 124 slots, we also have a subdivision into compaction bars. Again, compaction is also something you cannot get away with. Sorry about that. And now we will see, okay, subconsciously I've made this divisible. So because 124 is evenly divisible by 32, because like why would you use anything except power of 2, there is an even number of compaction intervals inside of a checkpoint. And compaction interval actually like defines that data gets written to disk. So like in compaction pacing, we learned that actually we write data to disk incrementally, but logically, you could think that each of these red squares represent a particular packet of work which we persist to disk. So after, like in the middle of a green square, the state of disk is somewhat indeterminate, like we are deleting some tables and appending new tables. But in between red boxes, the state on disk is like deterministic. It's kind of like includes all the transactions up to this point. So, for example, if our log is somewhere here, and our compaction is here, then we know that hey, everything that is before the red line is fully reflected on disk, but it is not the latest information because we have these extra pre-prepares on top of it. So we know that to get the actual freshest data, we need to take the data from disk and append these extra free things on top of it. Okay, so now we know that our journal is finite, that we only have like 1K entries. So once we reach the end here, we are going to, so when we write something like logically here, what actually will happen is that we'll go and we'll overwrite this old slot and write a new slot on top of it. Okay, so before we do that, we want to commit all our state on disk so far in the superblock. So when we are nearing the end of our journal, what we do is that we then compute the new root pointer, compute the new superblock, and write this new root pointer on disk. If we have successfully written our new root pointer, then if we crash and restart, we start in the new state and we won't be replaying our log. If we crash before we updated this root pointer, then, well, we start from the previous checkpoint and we go and replay our entire log rather than just like very few prepares at the top of the thing. Okay, so this is the general setup when it all works as expected. Now, what happens when things do not work as expected? What happens if, like, there is like a bunch of replicas and they processing requests normally, and then like they are like somewhere like in the op like 100 and 100,000. So this is like pretty far in the lifetime of a cluster. And then after being partitioned for a long while, or after being down, or like for some other reason, like Replica joins, and it has like say it is. Now I want to move this thing. It's here. replica joins, and it has something like, op equal like 92. Well, let's actually, okay, let's start with a simpler case where it's like not 92, but maybe like 99,099,602. So this replica misses just 8 ops to get to the top of the cluster. Then what happens is that the normal repair protocol kicks in. So in this situation, the replica, so it doesn't have this, no, I don't want giant rectangle, I want just to select things. So it doesn't have, no. How do I delete things? Okay, it doesn't have this prepares. So in this situation, a replica goes to a node which does have those prepares and says, hey, could you give me prepares? And then those prepares are transferred back. So let's look how it works in the source code. It is relatively straightforward. So replica has repair function which runs the repair protocol, and the first thing it does is that it checks if it knows the checksum, a cryptographic checksum of the content, the header for the latest prepare that it knows should exist in the cluster using like previous information from a primary. And if it doesn't know like the latest message, it sends like a request start to you to the primary, and the primary then tells this replica about the latest here. Otherwise, if it knows the latest header, then it also checks that it has all the headers before the latest header. And again, if it doesn't have this header, it sends a request for headers to any other replica. And given that it learned the latest header from a primary, it can actually check via hash chaining that the remaining headers are correct. Okay, and now once it has all the headers, it then goes and requests any prepares which it is missing. So it looks at the header which says which prepare it should have. Then it looks at the journal and checks which prepare it actually has. And if there is a mismatch between what it has and what it should have, so meaning that it has prepare from like the past wrap of a journal, it asks for prepare from the primary. And this is like normal repair protocol. And it works as long as there is some intersection between replica's old journal and the most up-to-date replica. So like, if like you say like this prepare is like blue and this prepare is blue. So in this situation, okay, let's remove this thing. No, that is a bit too much. Okay, so in this picture, like this replica has like full log, and this replica has almost empty log, but still there is like this one prepare in common. So this replica could transfer every single prepare and then reconstruct the state by replaying prepares one by one. Because again, when that up-to-date replica was at the place where it accepted the blue rectangle, the blue prepare, its state was exactly the same as the state of the replica below, because we do have determinism in our state machine. So that means that by replaying all those prepares, the replica below could actually get to exactly the same state. But now, let's say that something pretty bad happens. Or, well, actually, it's not bad, it's normal. So this replica adds a prepare to its journal, but it is the end of the journal, so it actually goes and overrides the previous prepare, and now that is not the blue prepare, but now it's actually like the orange one. And now we are in trouble. Well, okay, maybe right now it's like we are not exactly in trouble, but let's say situation is this. So there are like a couple of prepares. Well, and now we are in trouble. So let me pop this one slightly above, because like to replay the log on the replica below, we really need this prepare. Like we need this one, but it is already overwritten on our replica, which is more up to date because it has only finite log. So if a replica is sufficiently far behind, it might not be able to catch up using log repair. And what needs to happen here is that we need to trigger state sync, meaning that again, this kind of like this all happens at a particular checkpoint. So this is log, and let's say that we have this orange checkpoint here. Now, the checkpoint for this replica is actually going to be a blue checkpoint. So we know that it's definitely going to be not an orange checkpoint. Because if two replicas have the same checkpoints, then they are guaranteed to have intersecting logs, because the length of the log is simply less than the length of a checkpoint. So if their logs are not intersecting, then checkpoints are necessarily different. And what we do in this situation is that, it's no longer possible for this replica to go from blue state to yellow state by replaying the stuff, because this thing is gone. So what we do here, we do a state sync. We first say to this replica, hey replica, please jump from your blue state to your orange state, and then wipe out your log and start replaying stuff using your new yellow state. And we could actually help to repair stuff using the yellow state, because, well, we do have we do have all prepares which were built on top of yellow state. Okay, so that is the essence of state sync. Rather than reconstructing the state by deterministically replaying prepares, we just transfer the entire state. And this is where we come close to one of the most beautiful aspects of TigerBeetle. So in general, state sync sounds like pretty bad, because I mean, state could be terabytes. So you actually, worst case, you would have to transfer a lot of data between the two replicas to make the state match, which is pretty bad. But remember that all our data is a persistent data structure. So this orange checkpoint is just essentially like a root pointer. In other words, it contains some block addresses and block checksums, which point to the actual state. So that actually means that it is relatively easy for us to implement the logical state sync. We just say, okay, let's transfer just a root pointer to to this other replica. And we are kind of like that. We haven't transferred the actual data. We transferred just a checksum of the data. So that kind of like means that, hey, this backend replica kind of like doesn't have anything. Like, I mean, we transferred one checksum. But on the other hand, it sort of kind of like has everything, because what we have transferred is the root pointer. And now, like, now that it knows the root pointer, it can get some data from somewhere and check if the checksum of this data matches the checksum in the root pointer, and if it does, it knows that, hey, this is the state. So this is the first thing, that like logically state sync is just syncing the root pointer, which is easy. Now, there is a second aspect to this, and that is that, as I've said in the beginning, TigerBeetle assumes that the storage fails. So there is this state repair protocol which transparently fetches data from disk if it is not found there. So again, we've seen this before. If we go to the grid, we see read block function. Well, actually, let's let's go to compaction, to our favorite code. So read block. Okay, so we are like calling a read block on the grid, and we're passing the callback here, and the callback doesn't take possibility of the error into the account. The callback receives just the block. It doesn't receive a block or an error. And that is because inside the grid, index block callback. Inside the grid, if we actually fail grid read, let me check this. So we do a read. So then we go to the storage and read the actual block from disk. And then if the result is not valid, we kind of like okay, where does this happen? Okay, we call grid block result with result. This is inside the grid, so inside the grid we know where the read failed or not. Okay, so if the result was not actually wait, no, is this okay? So I'm losing it. Okay, result is valid. Here are just the asserts. Okay, yeah. So if result is not valid, then we don't call the callback with like, hey, this is wrong. We kind of like just push the read to a queue. And then we push that queue onto a queue, like a global queue on the reads. So this is the list of reads which errored on our local replica. But it doesn't mean that, like, it is game over, because this read global queue, periodically we are going to yeah. So because like we just put those reads, like, as they are still executed, and periodically the replica periodically the replica will ask a grid, hey, dear grid, what are the blocks which you tried to read from local disk and failed because like there is some kind of an IO error? And at that point, we'll like go and return the checksums and addresses from this queue. And the replica will take these checksums and addresses and will send a request block message with with addresses and checksums of this block to some other different replica. A different replica will go and read the block from its local storage. And if it checksum checks out, then the block will be sent to the original replica. So the block will, the replica will get called on block, well, replica. So the original replica, which had trouble reading blocks from disk, will receive this block from some other replica and would say to the grid like, hey, sorry, I'm going to sneeze, or maybe not. Tells to the grid like, hey, dear grid, I've just read this block from other replica, at which point the grid will look at its like global queue and see if there is a block which matches, and if that block matches, it will try to like call this grid, this read resolve function again, which this time will go into valid case and invoke the callback, and back in the compaction we actually will get our block. So in other words, when you read data from grid, you don't care whether you read this data from a local block or from the remote block. And that means this is beautiful, because this means that actually, like, you know, our entire state sync algorithm, which looks like it's going to be like hugely complicated because it needs to send the entire state, it's actually just transferring the root pointer. Because, like, you know, you transferred the root pointer and that's it. And then, like, you know, this replica tries to dereference with root pointer, tries to read some block from grid, and the block isn't there. But it's not a problem because it will try to request this block from a neighboring replica, and it will try to request this block from this replica. This replica will go, and because it is on the same checkpoint, it has this block, so it will transfer the block to original replica, and that's it. And then it will try to read the next block, etc., etc., etc. So that is the magic. You only have to transfer the root pointer, and then you are done, because everything else is going to be transparently handled by the grid repair protocol. And this magic actually motivates all the suffering that we had to bear while we looked for many episodes into the compaction code. Because what is the precondition for this trick to work? The precondition here is that the data is physically identical on different replicas. So it's not enough for this to work out that replicas store logically the same data in their data files. No. Because we use content checksums to address blocks, it actually is important that checksums match across replicas. So the actual blocks on disk are exactly the same. And that means that replicas need to behave fully deterministically with respect to disk, and that means that replicas must run compaction in a deterministic manner, which means that we need to have this like hugely complicated compaction dispatch loop, which enforces determinism. Okay, but now that we actually have it, our job for syncing the state reduces to two things. The first thing we should do is that we need to sync the root pointer. And the second thing, well, I kind of explained to you that we are done at that point because then we'll just, we'll repair blocks as we go, as we're trying to read this. But actually, if you try to think about it, it's potentially going to be pretty slow, because your block usually form some sort of a chain. You read one block to read another block to read another block. So you read manifest block to get the index block, and then you read the index block to get the data block, etc., etc. So if every one of these triggers a repair protocol, you get this long sequence. You basically you have to repair them sequentially, because while you are repairing manifest log block, you don't know which index block and which data block you need to repair. So that's why actually we kind of want to speed up this repair protocol. We want to try to run ahead of our read request from compaction from a state machine and try to eagerly see what blocks I need to repair. And that is actually done, and that actually reminds us another thing that we need to do periodically. So basically, the idea here is that instead of waiting for a while we need block, we'll just eagerly request all the blocks we might need to actively trigger the repair for the checkpoint to sync the content. Another thing another process in a database where you need to periodically proactively read the blocks is so-called scrubbing. So you store data on disk, and you assume a reasonable real-world model that persistent storage sometimes fails, that you wrote some bytes to disk, and the bytes are there now, the bytes are going to be there tomorrow, and probably a week after they will still be there, but a year later they might actually already be thrown. Probably they are going to be there. Disks are pretty reliable. You wouldn't get a storage fault just because you store data for a year on disk. No, that wouldn't normally happen. But it could. At a large scale, if you store a lot of data, if you have a lot of disk, some byte somewhere will get corrupted. So the way to combat this is that you go and you periodically read all the data on your data file, so that if at some point you do find that there is a corruption on disk, then you go and ask some other replica for a correct copy of this file. And this process is called grid scrubbing. So periodically, we scrub the entire grid. We don't do this very fast. We want to scrub grid a couple of times a year, maybe. But still, we kind of want to do this eventually. And we can plug this same process into our grid, into our state sync. So after we transfer the root pointer, we could also poke our grid scrubber and say, hey, GScrubber, I know that you're lazy. I know that normally you run very, very slowly, but it so happens that right now we have synced our state. So probably we actually are missing quite a lot of blocks. Could you please just speed things up? Could you just read more data from disk so that we repair it quickly? Okay, I guess this is more or less everything I wanted to cover today. So just a big picture, Xcalibur drawer, state sync algorithm. And next time, and probably even like next time, we'll look at how this actually happens in the code. How we go and transfer root pointer, how we decide that we need to state sync in the first place, and how we decide when we end it with state sync. How we figure out that not only we have the root pointer, but we actually have the data, because this is important. Okay, so this one I cover here. Like the danger of this like only root pointer state sync is that, like, you know, you could have like 5 replicas, and each of the 5 replicas said, okay, I have state, but what they actually have, they don't have the state. They have only a root pointer, and the actual data is like missing. So you could have like false confidence that your data is replicated while actually it is not. So it is important that this lazy state sync protocol doesn't actually falsely compute the durability. And that we'll also look at next week on Thursday at 5 p.m. UTC, live on Twitch and on YouTube. So thanks again for joining, and see you in exactly 1 week minus 1 hour. Goodbye.